Hello, welcome to this workshop on graph computing. My name is Yadong Li. I'm the CTO and co-founder of Julius Technologies. Today, my colleagues and I are very excited to meet you here and to explain the key benefits and ideas of graph computing. So in the past 17 years also, I have built some of the most complex models and systems for big banks and have accumulated a lot of experience in dealing with enterprise systems. So in this workshop, we're going to explain why graph computing is such a game changer for building complex data and analytical systems.
This is the agenda for today's workshop. First, I'm going to make a short presentation covering the basic concepts and the key benefits of graph computing and why it's important. Then we're going to go through a benchmark study showing some of the common platforms available to Julia and Python developers, and do a benchmark study of these different platforms. Then we're going to use some of the real-world examples to illustrate how to build complicated, large-scale, and realistic graph computing solution using Julia's platform. So at this part of the presentation, my colleagues from Julia's Technology will be joining me. So first, what is graph computing? Graph computing actually is a part of this broader field called graph technologies. Graph technology has recently been trending, attracted a lot of attentions. Gartner forecasts that 80% of data and analytics innovations will be made using graph technologies by 2025, up from 10% from 2021. So this is a huge forecast of growth and a huge vote of confidence by Gartner. So there are several different categories of graph technologies. So for example, people are most familiar with our graph databases and such as knowledge graphs. So for example, if you look at the social network, the data can be organized as a complicated graph. So the second category is graph analytics or graph ML. So this is really about how to write algorithm to analyze the graph. For example, find the shortest path, try to find ways to dissect the graph, and also try to see if graphs are connected, nodes are connected to each other. However, these are not the key, the focus of today's workshop. Today's workshop is about the graph computing, which is about how to build systems and applications as graphs. So the platform that in this space include Dask, Airflow, PyTorch, TensorFlow, Dagger.jl, and of course Julius. So these software provide ways to build complicated systems and applications as a graph. So first question you may ask is, why do we want to do that? Why do we want to build a system as a graph? So this goes back to the point we mentioned earlier about enterprise building enterprise systems, in particular enterprise data and analytics. So for people who have worked on enterprise software, you can appreciate that the enterprise software is a totally different animal from your desktop application or mobile application or even web application, because they tend to be like complex, very opaque, heavy, and also these systems tend to run for a long time. Many of them run for decades. They accumulate tons of technical debt and entropy over time. They tend to become overly complicated, bloated, difficult to support, require an army of developer to maintain and keep it up to date. So if you look at why the enterprise system is so difficult, so expensive, of course, a part of the reason is the organization itself. Like that, certainly bring a lot of complexity to the systems. But if you focus on the technology side, I summarize these 6 different challenges purely from technology point of view. We call scalability. We have acronym for them called Stellar. They particularly named. They particularly are scalability, transparency, explainability, lineage, adaptability, and reproducibility. So of course, these 6 are not an exhaustive list. There are many more challenges, but we think these 6 are really the key difficult challenges to solve in enterprise computing world. And if you look at these 6 different challenges, to solve one of them is not easy. To solve all 6 of them together is a very tall order. So the reason why a current enterprise system becomes so bloated and difficult, complex, a big part of that is the current development environment or platform doesn't supply general solution to the Stellar challenge. So therefore, it leaves the task to individual companies to have to build these solutions on their own. So these ad hoc solutions tend to be inadequate, like probably not consistent, and also not optimal. So as a result, the system becomes more and more complex when you add more and more of these requirements and features. So how graph computing can help? So this slide shows a very high-level summary of the key difference between the traditional programming paradigm and the graph computing paradigm. So in the traditional programming paradigm, we write a lot of code as functions. Basically, if you look at any programming language, it eventually comes down to a collection of functions. These functions can be compiled into binary code, then they will be executed by a runtime. So the runtime can be a single process or multiple process running on cloud. It doesn't matter. The key point here that the runtime, after executing your code, give you the results magically. Hopefully, it's correct results. But however, the runtime tend to be a big black box. It doesn't give you any insight on how the results were produced. It doesn't give you the intermediate results. It doesn't give you visibility to any of these like input output throughout the entire logic. So if you want to track or log some of these intermediate results, the programmer has to make an effort either to log it somewhere, a file database, or attach a debugger to see the intermediate results. So it makes it very difficult to understand the system and also make changes. So in comparison, graph computing works in a different way. So it starts with some kind of graph programming format or syntax. So for example, some graph programming solution use the drag and drop GUI to create these graphs. Most of them follow certain API to create graphs. So once we have the graph programming that defines the logic, we don't execute the code directly. Instead, we create an intermediate representation called the computation DAG, which is a directed acyclic graph. So this DAG basically captures all the logic flow of your application or a system. Then this computational DAG will be executed to give you the final results. So the key difference is that we have this intermediate representation called computational DAG. This is tremendously useful, and it actually later on in the next few pages, we're going to show how to solve the Stellar challenges we listed in the beginning. So in this slide is a quick explanation of what DAG is, computational DAG is. So we have a piece of regular code, and on the right-hand side, we have the corresponding DAG representation. So the computational DAG is basically a graph with directed edges, but without any circles. So basically, any program or systems logic reduced to a DAG representation. So the DAG is a very generic representation, regardless of how complex or simple your computation or system is. It already conceptually reduced to a DAG representation. So for example, if you look at a simple Excel formula on a few Excel formula connected on a spreadsheet, that is nothing but a DAG. Also, when you see these complicated IT system diagram, you notice these complicated arrows and boxes. That is nothing but a DAG as well. So therefore, like regardless of complexity, they all reduce to a DAG. Another point is also extremely important. Is acyclic. So when the DAG is acyclic, it guarantees that when we execute this DAG every node is only hit once because there can be no circles. So therefore, this is a very useful property compared to the traditional programming language in functions, which is are permeated with loops, if conditions. That make it much easier to infer its runtime behavior, because when you have a loop, you may looping over a variable that determines your number of iteration. So just before the execution of function, you have no way of knowing how many iterations that loop will iterate over. But with the DAG, if you iterate n number of loops, it will create like n subgraphs. From the graph topology, you can easily see and estimate the computational resource and the cost of that computation, make it much easier for the machine to optimize and analyze and distribute automatically. So this is really the key benefit of having a computational graph. So this page really answers the previous question, like why graph is such a great solution and generic solution to the stellar challenges we mentioned earlier. So first, the DAG is a generic representation. Any computation is reduced to DAG. Secondly, we already mentioned that for example, the DAG is great for distribution scalability, because you just need to write one distribution algorithm that works on any DAG, then you have solved all the distribution problem for all the system that can be mapped to a DAG, which pretty much covers everything. And also the other challenges, transparency, explainability, and lineage, all of them come for free within a DAG, because the DAG has the full information about how the data flow from one node to another, how the computation logic works on individual nodes, and how the final results is computed. So the last, adaptability and reproducibility, these are a bit more challenging than the previous challenges, because, for example, first, let me explain what they mean. So for adaptability means that when you have a complex system, it should be easy to make changes. So it shouldn't take a lot of effort, write a lot of code to make changes to your systems. Reproducibility means that you should be easily create copies of your system, and to use those copies to do experimentation and run different scenarios. So in practice, it sounds easy, but in the enterprise setting, it's incredibly hard, because for a complex organization, oftentimes they have one gigantic production system that is so complex, costly, or they're too expensive to support. To make identical copies of that system most of the time is out of the question for most organizations. And to make changes for a complex system, actually, you need to touch many components of the system, potentially running on thousands of computers. It's a very difficult job to coordinate and plan that change. Oftentimes, even simple changes can take months or years to implement. So just having a graph solution is not going to be adequate to solve the adaptability and reproducibility problem. So what we need here is really a low-code way to define your graph logic. So if we have a way to create a graph solution that is also low-code, then we can easily take this low-code representation of your production system and recreate it anywhere. Or we can take this low-code representation, make modification to this using this low-code representation, and regenerate the system with the new functions and features. So therefore, the key point here is that in order for the graph solution to really completely solve for the stellar challenge, we need to make it low code. So we have to add a L to the acronym to complete the stellar word. One of the L is for lineage, another is for low code. So this is really the key message you want to share in the first part of the presentation. So this slide highlights what Julius technology does. So I promise this is the only slide with a bit of information about us. So Julius offer a auto-scaling low-code visual graph computing solution for building transparent and adaptable data and analytical pipelines. So Julius is a generic stellar platform for building enterprise systems. It allows enterprise to build a stellar system at a fraction of time and cost. So I see in the comment there are some comments about the examples. So we're going to have plenty of examples in the rest of the workshop. You'll see how it works. in practice. So basically, here what we provide is a generic development platform that already have the stellar challenges solved, so allow developer to focus their energy building the business use case. And for Julia developer, this means that we provide great tools for Julia developers to tackle complex enterprise problems, where we see Julia can have a tremendous opportunity and the need in that space. So now let's move on to explain a bit better on this low-code graph programming point. So of course, graph computing starts with some kind of graph programming method. So how you do your graph program actually have tremendous importance in the performance and the characteristic of your graph computing solution. So for example, here we can quickly say that any GUI-based solution, drag and drop solution is not going to scale because you cannot drag and drop thousands of nodes and create a graph from that. So it has to be some kind of programming approach for the graph solution, graph computing solution to work for enterprise settings. So in this case, here we are showing like how the typical way of creating graphs, like a typical graph programming approach, and also the Julius low-code declarative programming approach. So in the conventional approach, how we create graph, for example, this is the approach that followed by like a TensorFlow, like Airflow, all of the typical current graph computing platform is you write in traditional programming languages, most likely Python, with some special API, most likely Python decorators. And once Python code is executed with this special API, instead of computing the numbers, it actually records the logic of that computation in the graph, do a lot of housekeeping and keep track of the information in the graph so that it can be executed later on as a DAG. So this is a typical recording approach. So the Julius low-code like graph programming approach actually is based on a DSL, domain-specific language called root DSL. It's a very simple declarative syntax, only with minimum features. It is specially designed for graph creation. So because when you do the standard recording approach, you have to like run the entire program from beginning to end to generate a graph. In comparison, when we generate a graph from root DSL, that happens directly. It doesn't have any intermediate. We don't have to run the program from beginning to end to create a graph. So therefore, the graph creation using root DSL is orders of magnitude faster and much more memory efficient. So let's like probably dig into a bit more detail in this point, which is the important point I want to explain clearly. So when you write graph logic in the conventional programming language using like the typical recording approach, you basically writing with the full general purpose programming language features such as like types, classes, functions, loops, and branches, polymorphism. All of that are at your disposal. So this is a very complex set of language features. But if you look at the final output you want to produce, it's a computational DAG which doesn't have any of these features. It doesn't have loops. It doesn't have branches. It doesn't have polymorphism. It's just a computational DAG which pretty much like or with all of this information removed. So if you look at the traditional approach, so in this case, you write a lot of code and then just make a lot of effort to write the graph logic using the traditional programming languages, then only have to have them like undone, the effect undone removed in order to create a computational graph, because you have to run the entire program to record them. And also you have to unroll the loops, like you have to resolve the branches. You have to remove the map out the polymorphism. So this seems to be a lot more wasted effort. So the reason you're doing like unnecessary work on each of these steps. So the reason that you're not creating the graph using the right tools. You are using something that is not designed for graph creation. So in comparison, using the root DSL, we have a low-code syntax that directly map to the graph topology. It just defines nodes and dependencies. It doesn't support many of the complex language features like functions, loops, if statement, whatever. But it does support polymorphism, because that is, we do want to build different pipes according to the different data types. That dynamic behavior is important. So therefore, it's much simpler set of features in the root DSL, and it make it much easier to create a graph, because pretty much this root DSL can be directly mapped and expanded to graph without much additional process. Compared to the recording, you have to do a lot of work to unravel your traditional program language into graphs. So this is also I want to make another point, which is if you look at the Stellar challenge, we want to solve this Stellar challenge end to end. So once you have the computational graph, some of these Stellar challenges can be solved. For example, distribution can be automatic. But if you look at end to end, this part, this part cannot scale and cannot be easily distributed, you haven't solved the Stellar problem end to end yet. So this is one of the issues with the traditional graph programming approach. For example, if you create a very large graph that can have hundreds of millions of nodes, when the graph becomes very large, the bookkeeping information also grows. The recording that graph can be much more expensive than like executing that graph for very large graphs. So in this case, for the graph to scale to the enterprise level, you have to solve the parallelization and also the same Stellar challenge for this graph creation part. So this is another point I want to make. So therefore, rely upon the traditional recording approach actually only solve half of the problem. Like this part still remain challenging, like unresolved. In comparison, go with the root DSL, we solve the entire end-to-end, like from the graph creation to the graph distribution and execution. So now let's quickly back up the claim by sharing some of the benchmark studies. So here, this is a comparison between Julius graph engine and a few very widely available graph computing solutions. We did a benchmark that using a simple example, which we're going to show a bit more detail later. But here the point is that when the graph size increase, many of these alternative graph computing platform cannot handle the large graphs. So none of them actually managed to finish the execution of 500,000 graph within reasonable amount of time. I waited 6 hours, couldn't finish, I have to stop. But for Julius, its orders of magnitude faster in terms of graph creation and execution, only take 15 seconds. So that's actually not a typo. 15 seconds to create and execute the graph of size 500,000, which is many orders of magnitude faster than the rest of the comparison alternative platforms. So at this point, you may think that yes, it sounds interesting, but does it mean that in order to use your graph computing solution, I have to code everything I have using your root DSL? That is typically not the option at all, because you may have complicated library that already have been battle tested for years. It's just too valuable to throw that investment away. So I think the key point here is that you don't have to recode everything you have using the root DSL. So what we provide is a very simple atom interface. We're going to show later on in the examples that give the very simple interface to interact and interop with the traditional programming languages. So for example, when you have Julia, C, C++, Python, .NET, Java, like the typical mainstream programming language, you can pretty much like plug in your libraries into this Atom interface. So the difference between the root DSL and Atom is that the root DSL governs the creation of the entire graph pipeline. But in terms of what's happening at individual node, that is determined by the individual atom. So basically every rule in the root DSL refer to atom that basically specify what logic to apply in individual nodes. So in this case, the atom is named obviously after atomic, meaning that it only affects one particular node. It doesn't affect any other node in the graph. So once we have these two construct defined, then Julius graph engine will take them and automatically generate their entire system according to the logic graph programming in root DSL and also the atom functions or atom objective defined interfacing with traditional programming function style of programming. So this is this actually makes the entire system building like a much easier because the system is created, the entire pipeline is created for you. You don't have to write a lot of imperative code to create the system. So I think this is a quick conclusion of this part of the presentation. So the low-code graph programming, if you take away one point at this point, is really a critical ingredient for graph computing to realize its full potential. By adding this low-code feature into graph programming, we actually offers a generic solution to the stellar challenge in building enterprise systems. So at this point, I'm going to quickly walk through a bit more detail of this benchmark. And then later on, we're going to go through some detailed tutorials to show the root DSL syntax and the atom interface. So this benchmark study actually is quite straightforward. So basically, use a very simple Fibonacci sequence type of calculation, and also we computed the summation of all the even terms of the Fibonacci sequence. So in this case, to make it more interesting, instead of running on scalar, we run them on a vector of length 10. So as you can see, when you increase the terms here, you get like a y, which is a very narrow but a deep graph. But as the summation of the even terms is very like both deep and wide DAG. So of course the deep and wide DAG is more challenging to execute, to orchestrate. So then we use different graph computing solution to solve these two identical problems, and look at their timing. So the timing we already reported. It's a dramatic improvement to have the root DSL. So here we're just going to quickly look at the code. So this is a Dask implementation. So basically Dask, as you can see, uses decorators so to decorate the Python function. So with these decorators, when the Dask runs, it doesn't create the results right away. Instead of it adds information to the graph data structure and all the housekeeping information so that it can be run in a distributed manner later on. So very similar, Dagger JL has a very similar approach. Like we have this spawn macro that specifies the task will be recorded on the graph and run later on. And also the TensorFlow implementation is similar, but it has a decorator like this. So the last, we're going to cover the Julius implementation in more detail in our first example. But before we do that, let's just quickly show how to sign up for the Julius free developer website.
From this GitHub page of Julius Graph, you can find the links to sign up to our developer website by simply click this URL, and enter your basic information, and agree the terms and service. Follow the steps on the screen, and you can find a Jupyter Lab environment where all of the tutorial notebooks we are going through today can be found.
Okay, right. So I think now let's probably see if we have any questions from the audience. To ask questions, please use the Pigeonhole link. Okay, I see some questions already being answered. Yeah, there's a question about how a relatively small research project benefits from graph computing, or is it an overkill? So it's harder to say in general, but I think it's true that the bigger systems and bigger applications will benefit more from the graph computing. The smaller project tend to benefit less, but if you're oftentimes the smaller project have a potential to grow in complexity. So at some point you may want to revisit that decision. Okay, so I think we have the questions answered. So let's go through the first example, which I'm going to walk through the key syntax of the Julius DSL and the Atom interface that to interface with the traditional programming language. So just one quick point to make is the Atom is also a great way to control the granularity of your node, your graph, because you can have a atom that does heavy processing, a heavy atom. That means your graph will have fewer nodes for the same task. Or you can have atom that is very granular, does a little bit of work. Then your graph will have a lot more nodes. You have full control of switching the logic between the number of nodes, trade them off between number of nodes and what did happen in each individual node. So here, in this tutorial, we're just going to highlight the key syntax for Julius DSL and Atom, and show how easy it is to implement the Fibonacci sequence we shared earlier in the benchmark. So the Julius Atom is a very simple abstract struct defined in Julia. So here is a very simple atom that is defined to compute the weighted sum of arbitrary number of data frames. This will be used to compute the Fibonacci sequence on data frames. So the atom is a abstract interface. Here we're using a struct from the base atom. It's called datum. So this is the most generic and commonly used atom type. It can capture any kind of data processing or numerical computation. There are different types of atoms that you can define. So for example, some atom interfaces are specialized for adjoint algorithmic differentiation, AED implementation, but that is not the topic of this part of the workshop. So if you're interested, you can get access to the web environment and also look at the AED example. You get all the detail there. So in this case, you can see that the atom just have a very simple interface, a single function called for data. Take the in this case datum object as the first argument, then take a arbitrary number of data frames, then just internally does a weighted sum and return a vector. So we choose to define all the atoms to return vectors to be explicit that any atom can return multiple objects. So if you want to return a multiple object in one shot, it's very easy to do following this interface. So here this is just plain vanilla Julia code, nothing special. And from that, you can easily see it does what it's supposed to do. When you have a few data frames, you can compute the weighted sum of them. Also, besides this vanilla, like plain vanilla Julia way of declaring datum, we also offer a macro to declare the same atom in a more compact form. So this is a pure syntax sugar to make it easier to write atoms. The reason there is benefit for doing this because if in the future we have to make an API change, then if you write your atom in the plain vanilla Julia code, you have to make corresponding changes if there are future API change. But if you're using a data macro, then we're just going to modify the data macro in one place, and all the data you declared using this macro don't have to be changed. So there is a benefit of doing it using the macro, so it's recommended. And then we declare another datum, which is just a random data frame with a different mean value specified as the first parameter. So in this case, this is pretty much all the syntax we have for the datum. It's pretty straightforward. And I don't think require any further explanation. The one point I want to just emphasize that the atom interface is implemented in all major programming languages like Python, Java, .NET, R, like what have you. So make it very easy to interop with the libraries coded up in other programming languages, or plug them. You can easily plug all of them and mix match them in the graph. So this part is really the key part I want to explain. This is the root DSL syntax that defines the Fibonacci type of operation on random vectors. So in this case, as you can see that first we use this another Julia macro add rules to define the root DSL. It takes a namespace. In this case, namespace, you can give it any name. We call it sequence, SEQ. So after the namespace is a begin end block. Within this block, you have a isolated number of declarations of your rules. So we call these basic logic unit rules. So pretty much, if you look at the syntax, for example, if you look at this core recursion definition of the root DSL, this part specifies the output node, the name of the output node. It can take parameters, and it can take this like a value-based templatized types. So basically, the output node is fully, it can be parameterized with different types. And inside, you can have a begin end, or if you just declare one line, you can drop the begin end. So this part ties the output to a particular atom. So basically, this says that the operation to be applied in order to generate this output is captured by this atom. And this atom, the square bracket syntax, will be directly translated into a parenthesis at runtime, so that the constructor of that atom will be called. So therefore, when you change the square bracket to parenthesis, this gives you a direct way to create that atom as part of the graph. And then this the atom is followed by a list of the upstream dependencies of other nodes in order to create that atom. In order to create that output node. So in this case, just the two previous terms of the Fibonacci sequence. It's very straightforward. As you can see that the rule syntax support recursion, and also in this case, the second parameter basically identify whether this node is a initial condition or not. If it's initial condition, then just does something special, like we just create a random vector for the data frame. So this is pretty much the core logic of the Fibonacci sequence definition. As you can see, like it's pretty straightforward to read. There's no complex syntax features, and this pretty much captures like probably the majority of the syntax available in the root DSL. And you can see that this is very different from traditional programming language, as ordering doesn't make a difference. So these are fully declarative syntax. So the rules are not executed one by one. Instead, at the runtime, we're going to recursively take one of the rules and expand its upstream dependency recursively, so that the entire graph will be created on the fly. So the other two rules actually just for convenience. So if a user didn't specify whether this is an initial condition or not, we just automatically inserted. In this case, the 0 and 1 are the two terms that are initial condition. And if the user give a floating point number, we just cast it to an integer and call the other rules. So in this case, you can see that we support the polymorphism. So the different rules can have different behavior. And also like this alias is a very useful atom that just delegate this, basically create a reference of this node to the input node. So it's directly pass through, allow you to organize the rules in a more readable manner by assigning different names. So this is pretty much all the syntax, the majority of the syntax in the root DSL. As you can see, it only takes like probably 10, 15 minutes to explain. It's a very minimal syntax, doesn't have any of the complex language features. So then later on, we can see how these rules are used to create the graph. So in this case, for example, if you want to create a Fibonacci sequence node with parameter 3.2, so what we do is use a fully qualified name with both the namespace and the rule name. So in this case, map to this rule. And we use this macro to bind a concrete parameter to this rule. And once we bind it with a concrete parameter, it become a node ref type. So basically, a node ref is nothing but a rule with every parameter binded with concrete values. So this uniquely identify a node in the graph because there cannot be, if you have two nodes with same rule and same parameter, they are the same, it's really the same node. It should only exist once in the graph. It should not have duplicates. So we guarantee that there's no duplications. And this is pretty much a very straightforward way of assign names to all the rules in your graph. It's tied to the root DSL definition. It's very convenient because it allows you to name any arbitrary rules and nodes in the graph. So once we have this reference defined, we just call these two functions to get a graph output, and the result is showing here. So we can also bring up a graph UI. So this is a very convenient interactive web UI that will allow user to visualize step-by-step how the data is produced and how they flow through the system. As you can see that this pretty much like straightforwardly follow the rules. So first we have a rule defined for floating point number, convert to integer number. Then we have that integer number depend on a version with two parameter, which is now the initial condition, and it continuously get expanded. Eventually you hit the initial condition. It's very straightforward to define the graph like this. Also in the graph UI, we have also can look at the rules, the dependency of the rules. So these are really the relationship between the four rules we have specified earlier. This gives a convenient view of your computation logic and also the underlying rule declaration the developer has written. So yeah, we already mentioned that this part. So once we have the node ref, it's uniquely name a node in the graph. We also can take a hash of that node ref to produce a unique ID of the node, so that the node can also be uniquely identified by the hash ID. So in this case, for example, if you want to directly query these two nodes, we don't have to search the graph, traversing the graph, can just directly run them by pick up the names and directly ask what is your value. So in the next part, we're just going to show how to handle dynamic number of dependencies, because sometimes the number of upstream dependency is unknown when you write the rules. It could depend on your parameter, or could depend on some other intermediate calculation you do. This is very like a rich. We want to support this type of rich dynamic behavior. So for example, in this case, if you want to compute all the even terms, the summation of all the even terms of the Fibonacci sequence, we have this language we have this like a syntax support of 3 dots to specify dynamic dependency. So basically anything before the 3 dots have to return either a node ref or a vector of a node ref. So that node ref or vector of that will be taken as a dynamic dependency of this node. So for example, in this case, when we declare we want to have all the even terms summed up, the dependency on the previous node is a variable like depend on the number of n. So in this case, for example, if you look at if you have n equal to 5, in this case there are 3 values. So this basically this entire vector will be replaced as the dependency of this node. So as a result, using this syntax feature, we can create a dynamic dependency like this, like sum up all the even terms of the Fibonacci sequence. Also, like you can declare local variables between the beginning and end block. So this time, sometimes this can be convenient if you want to do some quick data manipulation processing before you return the datum definition and dependencies. So yeah, this is pretty much all the root DSL language feature I want to introduce. So probably it hasn't covered everything, but it covered probably almost 90% of all the syntax we offer in the root DSL. Just a quick word before we move to the next session. As you can see that these declarations directly map to the graph construct. That is why it's so convenient and so efficient for creating large graphs. As you can see, it's structurally, it's like an output node, upstream input dependencies, and what you want to do in order to create that on this node in order to create that output. So even though this syntax is very limited, very minimal, but you can see that it can handle polymorphism, it can handle recursion, it can handle loops. For example, you have a kind of branches. So in this case, we do have different behavior for initial terms or non-initial terms. All of these rich language feature you may think you need, actually, we have shown you don't need any of those. You just need this simple plain declaration of rules that follow the structure of the graph, and you can do everything you could do in the traditional programming language. So the next part, we're going to introduce yet another very important concept called runtime and graph data. So far we have covered the root DSL syntax and how we can use it to create graph logic, and also how that can interface with the Atom and to interface with your traditional style of programming using functions. So just having the logic completely defined is not the full story of enterprise system. So any enterprise system have a rich set of configuration for runtime. So for example, whether you want your enterprise system to be like your system to be distributed, whether you want the intermediate results to be cached, whether you want to compute AAD along the way, or whether you want to run the entire system in a batch or streaming mode. These runtime configuration are not covered by your business logic or your analytical data logic. These are really how you want to organize, implement your system for the runtime behavior. So what's tend to happen is that, for example, in large banks, for example, since if you take streaming and batch as example, since these two different configurations have a very different requirements. Of course, streaming application wanted to be fast, and batch job you want to be like a scale and really process large number of trades very quickly. So we end up with often building like two separate systems for batch and streaming because their runtime behavior is totally different. So in this case, even though their logic ideally should be, their modeling and analytical logic ideally should be different, but they have separate implementation. That duplication drive up cost and make it difficult to support. Oftentimes your batch system and streaming system can go out of sync because they may follow different update schedule, create all kinds of problems. So in this portion, we show how Julius graph engine handle this problem generically. So basically, besides root DSL and Atom, that is really the two construct you need to define your entire business logic. We also follow the we also like we also offer another construct called graph data. This really encapsulates all the runtime configuration behavior you may want to do differently on the same logic. So here we support the three runtime configuration out of the box. They are all subtype of graph data. So far, we have been showing the usage of generic data. Later on, we're going to show a example of stream data. So the generic data is really like a batch configured for batch job. It by default have all the intermediate results cached. That is why when you go to the graph, you can see all the intermediate results at your fingertip. Become very convenient. So the stream data is really configured for streaming use case, and the numerical data. This is for the special use case of adjoint algorithmic differentiation, or AED. So if you want to compute AED in your end-to-end system, you're going to use the numerical data. It have native AED support. So also another point I want to mention that you can derive from this graph data and implement to your own runtime behavior. So for example, you may write a runtime behavior that doesn't do caching or doesn't do some of these things, or it's completely up to the user if they want to have a different use case other than the three we support out of the box. So the next portion is really showing how easy it is to take the Fibonacci pipeline. We build a very simple pipeline, turn that into a streaming job. So in this case, to make it more useful, we implemented Atom that simply compute the running average of all the data frames that are seen at this point, and we can connect this new data using a rule. So basically, it says that I want to compute. I can compute any nodes. I can connect to any nodes and compute its like a stream average. In this case, this is a very interesting rule because, as you can see, take a node ref as a parameter. So if you recall, the node ref is nothing but a particular node in the graph. So this actually declare a generic pattern, says that this rule can apply to any node in your graph and compute its like a running average if you're running the streaming mode. So this is another like very useful feature of Julius rule DSL, which are called high-level rules. So you don't have to declare like always declare concrete rules, but you can also declare generic patterns. So in this case, it's a generic pattern that you can basically connect to any node in the graph that does its thing. And this part, we specify how the streaming should be sourced. We take the first two initial terms as a source of streaming. Then we basically say we have the fifth term, and we are going to connect this streaming rule to that node, and we're going to run the streaming process. So as you can see that to convert your system into streaming, only need a few lines of code change. Specify the runtime configuration, then you get a streaming system. In this case, we stream like 20,000 data frames through, and it's very fast. Like 10,000 data frame only take 0.8 second. You get the average of these 10,000, running average of these 10,000 streamed data frames. Oh, sorry, 20,000 actually streamed, two batches of 20,000. So in this case, it's effectively we are computing the fifth terms of Fibonacci sequence using the Monte Carlo simulation. If you look at this end to end, so now we can look at how we can bring up the UI, and this is the output of the streaming. As you can see that the last node, this is the running average of all the previously streamed nodes. And if you look at the previous node, this is the value of the last data frame that has been streamed through. So therefore, the cumulative effect are showing in the last node, and the rest of the graph only cache the last value it has seen. So this is pretty much like the key highlights I want to go through for root DSL, and a very simple use case of a Fibonacci sequence, and also how to turn that into a streaming use case. So basically, the takeaway here is that really the syntax of root DSL is very simple, and it doesn't take much effort to learn and use. And also, it is very flexible. It gives you the ability to quickly turn your system into batch or streaming mode. Later on, we're going to show how to use distribution in the next part of the presentation.